students, welcome to the next video of ESR spectroscopy. Okay, so in the last video we learned so many examples with respect to the ESR lines and spectroscopy, G value, okay, land is splitting factor or spectroscopic factor. So today we'll go for the next concept. So one thing you come in the ESR, that is Dragos rule. What is this Dragos rule? So it says that the hydrogen attached to magnetically active nucleus or atom do not participate in splitting. This is called Dragos rule. So in the last video we have taken two examples, copper tetramine plus 2 and titanium hexaaqua. So where we have seen that the hydrogen which is attached to nitrogen, so copper I value nuclei, magnetic nuclei value is 3/2. Okay, and we have calculated number of lines here, how many ESR spectra, how it is got in the last video. But here nitrogen is 4 nitrogen, okay, and 4 threes are 12 hydrogen. But here hydrogen contribution for splitting is not there. Why? Because nitrogen is not a magnetically active nuclei. Okay, so hydrogen attached to magnetically active nucleus do not participate. So here the hydrogen will not participate. Why? Because this is a magnetically active nuclei. Okay, magnetically active nuclei. So that's why hydrogen attached to this nitrogen is do not participate. Well, while in titanium hexaaqua, so definitely hydrogen, 12 hydrogen is participating here because of the oxygen. So oxygen is magnetically inactive. Okay, magnetically inactive nuclei. That's why hydrogen will participate here. So 6 throughs are 12 hydrogen you have to consider half, 2 Ni plus 1. This and titanium you have to consider whose I value will be 3/2. So this is how we can explain this by the Dragos rule, and these two examples we have seen in the last video with respect to number of lines and all. Similarly, today's another example we will take it here, tetraaqua, diamine, tetraaqua, titanium plus 2. So how many lines? So as we will see here, titanium I value, okay, so is 3/2. We know that I of hydrogen 1/2, and nuclear spin of nitrogen is 1. Okay, we know this. So now we will calculate titanium 3/2. So titanium 1 is there, so 2 into 3/2 plus 1, 2 Ni plus 1, 4 lines. Hydrogen 4 to 8, definitely it will contribute because oxygen is an inactive nuclei. So 4 to 8, 8 into 2 into half plus 1, so 9. And lastly nitrogen 2 is there, so 2 into 2 into 1 plus 1, that is 5 lines. But here hydrogen is not contributing according to Dragos rule. So total if I do here, so how many lines now? 4 into 9 into 5, that is 180 lines. So 180 lines I am going to get in this complex, okay, the triaqua diamine titanium complex. Now here, so titanium is how many? So titanium you have to see here plus 2 state. So titanium plus 2 state means, so here it is D2 system. Okay, so you have to consider this also. Like in last video I have shown you chromium plus it was 4 unpaired electron was there. So here also D2 system 2 unpaired electrons is there. So no doubt 180 lines we are going to get by this 2Ni plus 1. But here titanium, since it is plus 2 states, so D2 systems 2 unpaired electron, that's why 2 into 180, that is 360 lines. It is going to show 360 lines. Okay, secondly, if you see here, ESR spectra have frozen aqueous solution of copper sulfate 5H2O. So here he has given copper sulfate 5H2O. So copper sulfate 5H, 1 2 3 4 5, okay, and one oxygen of this is been attached to the sulfate group here, like this is the structure here, and at 177 Kelvin. This is very much important, low temperature. So here copper, in this copper sulfate is in plus 2 state, D9 system we know, and here it is a static John-Taylor distortion. In the last video we have learned what is static and dynamic. So since it is static, what will happen now? So how will be the G value here? So G value in static, Z out. Okay, so if you see here, so it is elongated here, equatorial hydrogen as well axial. So axial bonds are elongated and equatorial is what inside Z in because of the John-Taylor distortion. And in this case it will be static, and since it is Z out conditions, what will happen here? Dx square minus y square will have the highest energy compared to the dz square, and dz square has 2 electron and x square minus have 1 electron. So here what will happen, since electron density at Z is more here, so always G parallel will be greater than G perpendicular. So in this complex, if they ask, so you have to write G parallel will be greater than G perpendicular. Why? Because of static nature of this Jahn-Teller distortion. Now if you see here germanium, one more case, third case. So germanium is there, okay, attached to some alkyl group here. So on photolysis, so you get here germanium radical, okay. So germanium radical, you know, germanium they have given the I value 9/2. Okay, so nucleic resonance here, spin here is 9/2 of germanium atom I value. So how many lines? 2 Ni plus 1. So you do it 2 into 1 germanium into 9/2 plus 1, it gives 10 lines. Okay, so this complex will give 10 lines of ESR hyperfine structure in the presence of photolysis, that is in the presence of what? Sunlight. Okay, so this is how. And one more complex we can see here, copper complex is there. So having nitrogen amine group here, NH. How many lines? So copper we know that it is having I value, nucleic spin value, that is 3/2. So you do again 2Ni plus 1, 2 hydrogen is there. Okay, so 3/2, that's 4 into 2 hydrogen is there. So just do it, calculate with a formula 2Ni plus 1. So you get 20 lines. So you are going to get for this complex how many lines? 20 lines. Okay. Now coming to the instrumentation part of this, so you can see here how the instrumentation part of this ESR is been a block diagram. So you can see here the source is there, then attenuator, then waveguide. Okay, waveguide is attached to the sample here, and they are placed in between the two electromagnets here. Okay, and there is modulation coil here, and this waveguide to sample which is attached to the detector. Modulation coil in turn attached to the phase sensitive detector, like this. So this whole thing will form the block diagram of the ESR spectra or ESR spectrometer, okay, or EPR spectrometer or EMR spectrometer, okay, electromagnetic spectrometer or resonance, ESR, EPR or EMR. So what is source taken here in this is the klystron. Okay, klystron tube will be there. So klystron tube will be there. So you can see this, that is not so important, anode cathode. So the klystron tube work is what? To generate the microwave. Okay, microwave source is generated here, and to then this is channelized to the waveguide. Okay, and what is the role of this attenuator? Attenuator is a role is to adjust the level of microwave. Okay, it will adjust the level of the microwave power, adjust the level of the microwave power. Then it is when to it will go to the waveguide. From here the sample, it will fall in the sample, and the sample cavity is of dual nature. Okay, so dual nature is means what? One is for the standard and one for the sample, which unknown sample, and one for the stamp or the sample, that is DPPH. Okay, so this sample will be in dual in nature, and this is been in between the electromagnets. Okay, so electromagnets, so ESR is recorded by slowly varying the magnetic field. Okay, by sweeping the current supply to magnets by power supplier. So this is the power supply will be there, and slowly ESR is recorded by slowly varying the magnetic field by sweeping the current. Okay, those current is been slowly swept here, and so while the magnetic field will be varying, and current supply by applying the sweeping the current supply to the magnets by power supply. Okay, and these two require, so that's why since it is very hot here, so these two systems require water cooling. Okay, the magnets as well as the power supply. Okay, so these two things are always survived by the water cooling. So some cooling is needed here in this case. Okay, both case. And then it will be modulation coil with respect to the sample. So modulation coil, it will modulate these signals here with also the phase sensitive detectors, and finally the detector will do its work by signifying the signals, whatever the changes is happening here because of the spin electron, unpaired electron spin, as well as the nuclei effect of the nuclei spin. So there will be whatever the difference will be here, so that will be detected with the help of modulation coil and phase sensitive detector. This will help, both will help to give the resonance very sharp peak here. Okay, and finally the detector. So detector is of the silica crystal, so it is made up of the silica crystal. Detector will be there. So like this, so whole block diagram will explain how the ESR spectra is working here. So main thing here, sample is very much important. We should have at least one unpaired electron. Okay, the spin, whose spin will be there, so electron spin versus the magnetic I value spin, there is the interaction between these two, and you are going to get the hyperfine splitting here. So number of lines will be obtained here, and that will be modulated as well as phase sensitized and then detected by the detector, which is a silica crystal, and you are going to get the fine spectra. Okay, you are going to get the fine spectra like in we have seen in what you say like this. Okay, so like this. So in fact are going to get like this two peaks, like in hydrogen we have seen, no? So in hydrogen atom, how many we are going to get? We are going to get two peaks like this. Okay, one and two peaks like this. Okay, so this is how we are going to get the sharp peak, hyperfine peak, like in all the cases we have learned. So this is how the we can explain the spectra. Hope you understood this instrumental part as well as some of the examples. So this, I think, hope here we complete the ESR whole chapter here. So nothing I have left here to explain more here. In the next video, I may go for again simplifying the splitting as well as how it happens, how the interaction takes place between the magnetic I value as well as spin I value. Okay, spin value. Okay, spin value as well as I value. So how they interact with each other and giving you hyperfine structure in the presence of magnetic field, in the application of the magnetic field. So I will simplify this also, so which will make you very nice understanding of the ESR EPR, and then we will conclude in the next video that will be complete, that we will complete ESR EPR. Next we will go for the Moss beer. Okay, hope you understood this. Have a nice time. Thank you.